In this series of videos, we're going to be learning about acids and bases and the chemical properties that allow the two to react with each other in order to neutralize each other. We're also going to be learning about a measurement system called the pH scale, which measures how acidic or basic a given solution is. In this video, we're going to focus entirely on the acids, using these two acids that we see below as the kind of exemplar acids of the two different families of acids that we're going to be looking at. From their structure, the fact that we can see that they exclusively contain nonmetals, hydrogen, chlorine, oxygen, and carbon are all nonmetals, and from the fact that they have line structure bonds, meaning that they share electrons, we can see that acids are, for the most part, covalent compounds. However, as we learned when we learned about ionization reactions, acids are a little bit unusual because even though they are covalent, they lose H+ whenever they are added to water, and this is what triggers the ionization reaction, which is what we'll review after we talked about the two classes of acids. So, in every acid, we can usually identify whether a compound is or is not an acid by looking at the first element, which is almost always going to be hydrogen, found again at the beginning of the acid's chemical formula, and we can see that in HCl. In this case, we can see that the hydrogen is bonded to a single other nonmetal, and again, the nonmetal is a requirement because acids, for the most part, are covalent compounds, and like HCl, the other solitary nonmetal is usually going to be some sort of halogen, so HCl is only one example. The others of the nonmetal halogen-containing acids are HF, HBr, and HI. Now, if these compounds were written with this formula, then we wouldn't necessarily know whether they're acting as acids, because remember that acids only lose an H+ when they are added to water, so traditionally the acid formula is accompanied by the state of matter aqueous, showing that acids are exclusively acids when dissolved in water. Now, if we take a look at H2CO3, we can see that there are more than two compounds here, whereas in HCl we only have two, and therefore we would consider HCl to be a binary acid, whereas this compound, because oxygen makes up the majority of the structure, because 50% of all of these atoms are oxygen, we can refer to acids like this as what we call oxyacids. Now, if we don't look at the oxygens by themselves, but look at everything that isn't hydrogen, we see that this is actually the polyatomic ion carbonate, and that's how we identify that an acid is an oxyacid, is that its structure will be based on a specific polyatomic ion. For example, if we consider the polyatomic ion nitrate that has a -1 charge, that means that there is going to be one H+ within its structure to balance out the -1 charge. Another example of an acid that has two H+ or loses two H+ ions in water is the acid that is based on the polyatomic ion sulfate, SO4, with a -2 charge, and we can see that an acid that has three H+ ions lost in water is the polyatomic ion, or the acid based on the polyatomic ion phosphate. Now, as a review of what an ionization reaction is, this is the type of reaction that acids undergo whenever they are added to water. Because acids are technically a covalent compound, it's wrong to refer to this compound as having an H+ ion and a Cl- ion, because again, hydrogen and chlorine are covalently bonded, meaning that they share electrons, but because acids ionize, this means that the water forces the hydrogen to separate from chlorine, becoming an H+ ion like this, and leaving the negative ion as the chloride ion like this, and here is our ionization reaction. Now, HCl only has a single hydrogen, so it can only release one hydrogen when it is in water, and therefore we refer to this as a monoprotic acid. So in terms of the root of this word, mono is obvious because it only releases one hydrogen, but the root of the suffix protic is actually the word proton, and we know that the protons are the positively charged particles that you find in a nucleus. Now, if we consider the structure of a hydrogen atom, hydrogen normally has one proton and 0 neutrons and only one valence electron in its first shell. But when H plus becomes positively charged, it loses this electron, and therefore H plus is only a single proton in the nucleus with no electrons anymore, and that's why we use the word proton interchangeably with H plus. And this is something that we will revisit in future grade levels when referring to acid-base chemistry. Now, because this acid, H2CO3, can actually release 2 H plus ions into water, because again, the polyatomic ion carbonate has a -2 charge, so we would require 2 H plus ions in order to cancel this charge. So naturally, this is what we call a diprotic acid, meaning that it can release 2 protons worth of H plus whenever it is added to water. Now, the polyatomic ion based on phosphate, because phosphate has a -3 charge, it would naturally be what we call a triprotic acid, because every one of these hydrogens in its structure can be lost when the acid ionizes when it is put into water. Now, all of this is fine and good, but how do you actually go about recognizing acids in daily life? Well, anytime that you have sampled a beverage that tastes sour, for example, lemon juice or particularly sour orange juice, you are drinking an acid. And for anybody who gets lemon juice or orange juice on their fingers, assuming that you don't want to waste it and don't just lick your fingers and get the citrusy goodness into your mouth, you'll find that you want to wash your hands, because acids almost always have a sticky texture, and citrus beverages, citrus juices such as lemon juice or orange juice, and we can also include grapefruit in this as well, are all examples of liquids that contain a large amount of acid. In fact, the name citrus is derived from the name of the acid that is found in citrus beverages, that being citric acid. Now, in most experiences of people that cook, the most common acid that is used by professional chefs is actually vinegar. And vinegar is an acid that we've looked at before. It actually has the chemical formula CH3COOH. And if we look at the Lewis structure here, CH3COOH. Now, this formula looks a little bit different because the hydrogen that is lost by vinegar when it is added to water is actually at the end of the formula rather than the beginning. And vinegar actually represents a third class of acids that we call organic acids, because vinegar is an organic compound, which is evident if we look at the central atom of the structure, which is carbon, which is usually a tell that we're dealing with an organic compound. Now, organic acids we identify a little bit differently than binary or oxyacids that we can identify just by looking at the hydrogen at the beginning. We can identify organic acids by the group that this hydrogen is attached to. So every organic acid in its chemical formula is going to have the 4 letters COOH, and we can see, if we write out the chemical formula for vinegar, we can see those 4 atoms right here, easily identified by this hydrogen that is the one that organic acids lose whenever they are added to water. Now that you have a solid background about the categories of acids, the next video will focus exclusively on bases as well as the reactions that occur when acids and bases react with each other.